And welcome to our official start of data structures for today. We, have a handful of announcements for us to do at the beginning, and then we're going to continue talking about binary trees, and in particular, we'll start talking about the binary search tree today. So let's go ahead and I'll share my screen. And the first announcement is that there's been a lot of questions, so both on GitHub, and I've gotten a number of emails from people about what the future course offerings are going to look like for upper division data science CS courses at CMC. So here is sort of what the current tentative schedule is going to be for the next 2 years. And the 2021 fall semester is pretty much set in stone at this point that we're not going to be able to offer any courses. Basically, due to coronavirus reasons, I agreed to not take paternity leave this semester, and so that I could keep teaching, and I'll take it next semester. And so because of that, there's not going to be any upper division courses offered in the fall. The current plan is that in the spring, we would offer big data. Big data is typically offered in the springs, and data mining typically offered in the fall. This potentially puts a number of students in a rough spot with especially students who are going to be seniors next year about how can you complete the data science major or sequence if data mining is not going to be offered. So at this point, the plan is that, or there is no plan to get data mining offered. It's going to be up to the administration to sort of work things out, and so that it's able to be offered. Definitely won't be in the fall, but hopefully we can do it in the spring. If it is offered in the spring, then it would be almost certainly me teaching both data mining and the big data class. Currently, for the professors that we have at CMC, it's only me who teaches any of these classes. There are, so before coronavirus, there was plans to have another hire who would also be teaching these classes, but coronavirus put that on hold. And so even though the goal is in fall, we'll be back to in-person classes, normal class schedule, coronavirus will still have some repercussions that way. There's good questions in the chat, and this is a question about probably on a lot of people's minds about if you are a data science major and you're currently a junior, so you'll be a senior next year, and you need these classes to graduate, are you just out of luck? And hopefully the answer is no, that we're going to try to get these courses offered. It'll probably mean either CMC will have to figure out a way to get a new instructor hired for the spring semester on a temporary adjunct basis, or they'll have to shift around a number of other course offerings. But the more, the more students who are affected by this, the more the administration is going to be obviously much more interested in getting this fixed. So if you do think this is going to affect you, please let me know so that I can have a list of here are the 2 or 5 or 10 students who are in this situation, and we can get this resolved for you. Another possible situation is that, so there's not an exact equivalent to our data mining course that's offered at either MUD or Pomona CS departments, but there are a number of courses that are very, very similar and could potentially count as meeting the data mining requirement. And so that's another option that's sort of being explored at this point. But that would require sort of cooperation between the different colleges that way. And so it's not yet clear exactly what that will look like. Raj, did you have your hand up for a question? Okay, thanks. Any other questions about anything
Yeah.
related to this? Yeah, go ahead, Justin.
So if to gather that list, should we just send you like a formal email, or I mean, I've already mentioned something to you. Is that like enough?
Go ahead and resend me an email just to make sure that I don't forget. And
Okay.
yeah, it's easy for me to forget things these days. As an aside, I know that a number of you have been sending me emails and GitHub issues about other things related to other topics. And if you don't get a response, I've tried to do my best to be on top of this, but easy for me to lose track of those things these days. And so if you don't get a response within a day or two, I definitely am not offended if you ping me again about it and keep asking about it. Please do that. Okay, so that's the first set of announcements. The second announcement's actually specific to this class. So just really a bunch of reminders about things. The first reminder is that your Twitter assignment is due this week. So a number of you have already completed that and submitted it, and so you don't have anything to worry about. But a number of you still have to complete that, and so please get that turned in.
Mike?
Yes.
I had a quick question about Twitter. How do we know that it's like that we've done it correctly?
Great question. And so, yeah, for all of these other assignments, we have these test cases that help you prove to yourself and to me that you've completed it correctly. For the Twitter assignment, there are none of these test cases, so there is no way for you to actually like have proof that you have completed it correctly. And one of the maybe sort of meta takeaways from this is that like you should really like test cases. They're very frustrating because you actually have to pass them. There's concrete steps that you have to pass, but you know exactly where you stand in terms of have you completed the work. And when you're working at a company in the future, whether you're a let's say you're actually a technical developer, software engineer, you want to receive requirements for a project that contain test cases embedded within them. And if you're maybe in a less technical role as a manager interfacing with clients, the engineers are going to want you to develop contracts with clients that have concrete test cases embedded in them. And if you don't have those test cases, it'll be very ambiguous to you and the client whether you've actually completed what the project is supposed to be about. So that's sort of a meta takeaway from this is just test cases are great. You should have them all the time. Okay, but absent test cases, how do you actually know in this particular case whether you have completed the assignment correctly or not? What I'm going to be looking for in grading on the Twitter assignment are, I'm going to look at your actual code. Have you done the modifications to the map.py file that I've asked? Have you created the shell script that I asked? And I'm not going to run it, but I'm going to look at both of these files and just make sure that the changes look reasonable. And then I'm going to look inside of your visualization outputs, making sure there's one for each of the results. And I'm going to just kind of spot check those results to see that they are in the right ballpark of what they should be. Depending on the exact details of your implementations, your numbers might be slightly different than the numbers that I got. So I can't tell you like, if you get this number, you know you're correct. But if you're off by say more than 10%, then it probably means that you actually didn't run it on a couple months or a couple weeks of the data. So you want to make sure that you have, in fact, run your code on all of the data. Other than that, there's no like concrete set of things that you can look at to make sure that you have the completed assignment. Dustin, go ahead.
Yeah, so for the countries, so it's not unlike the hashtags where we have like a a limited set of hashtags. There's like a bunch of different countries. Do we need to visualize them for each country or just like a handful?
So the countries and the languages are sort of equivalent that for, there's going to be two sets of visualizations, one set of visualizations for the countries, one set for the languages. And in each one of those sets, you're going to have a set of hashtags. So there'll be a file hashtag coronavirus that's somehow related to the, it's all the counting the tweets from each country that mentions coronavirus, and similarly, a hashtag coronavirus counting the number of languages, tweets in each language mentioning coronavirus. So there won't be any specific files for the different countries and no specific files for the different languages. Those will just get incorporated into the hashtag files.
Oh yeah, I think I misunderstood for a second, but that makes sense.
You also need to somehow make it clear that the like that any particular file is related to a whether it's languages or countries. There's a number of ways that you can make that clear, and it's on you to pick a way that actually makes it clear. It's also, I'm not going to be like grading your README file in particular, but you should put something in your README file so that if you're going to talk about this project with a future employer at an interview and they pull it up on their computer while you're talking, they have something to look at and ask you good questions about it. There's a good comment in the chat about a command that you can run, ls outputs pipe wc-l. This will check to see that you actually have an output file for each day in the original data set, and so it'll make sure that your program hasn't crashed on certain days and that you actually had it run on all of the days. So that's another good way to check your that your final project submission is correct.
Mike?
Yes.
I had a question about Sam's comment. Why is it 732? Aren't there 365 days in a year?
There are 365 days in most years, but not last year. Last year was a leap year.
Oh,
so
I see.
366, and then one for countries, one for lang, so times 2.
Yeah.
Yeah, so just another aside, like time is just a really confusing concept, and it's really easy when you're programming to have lots of bugs related to time. So yeah, leap years, relatively common, but even most people don't know all the rules for leap years. So like typically if a year is divisible by 4, it's a leap year, but the year 2000 was not a leap year. Years divisible by centuries are not leap years. Century years are not leap years. And then there's things like leap seconds and all these time zone issues. So anytime you're dealing with time, you should always just like assume that you're going to be doing something wrong and be very, very careful. Lots and lots of great questions. Any other questions about the Twitter assignment?
I had a question. Do you have just kind of like some general advice for Readmes?
Yeah, so my main piece of advice for writing Readmes is sort of the same advice that I would have for like writing anything, that you want to write what other people want to read. And in order to understand what other people want to read, you have to read. And so reading other people's Readmes is a good way to figure out like what are good things to put in README files? What are the things that you find interesting in other people's? You should put those in yours as well. For this particular assignment, I would just maybe like 1 to 2 paragraphs about overall what you did, and if there's a conclusion that you found that was particularly interesting, of like, oh, hashtag coronavirus was used a lot in April, it peaked in April, but then it sort of died down as other hashtags became more popular. I don't know, something like that. Yeah, so this project that we're currently working on, our homework assignment, that's this like big project containing lots and lots of different data structures inside of it. eventually what we're going to be building up to is you'll be making this an installable Python package that anybody can install using pip install. And for this project, we'll have a little bit more formal requirements on what the eventual README is going to look like, since it'll have to follow these guidelines for Python packages. But for the Twitter assignment, just 1 or 2 paragraphs, enough that somebody can quickly get the gist of what you did. Great questions. Any other questions?
Yeah, one more. Is it okay if our nohup.out file is empty, or is there like supposed to be something in it?
Good question. So for the Twitter assignment, I'm not going to look at the nohup file, and technically, this is a sort of file, something that I would call a build artifact of your program. It's something that was created while your program was running, and in some sense, it's output of your program because your program created it, but it's not the output of your program that we actually care about. Inside of Git repos, typically we would not normally include these sorts of build artifacts. We don't include other information that's not either the code to actually run things or the final end results. There's lots of good sort of reasons for that, which while we work on this larger project, we'll talk about exactly a little bit more in detail what should and should not go into GitHub repos. But yeah, the short answer for this is that I'm not going to look at your nohup file. I'm not going to look at your outputs file. The only thing that I'm going to look at is your code and your visualization. And anything else can be whatever it is. Whether it's there or not doesn't matter. Great questions. Any other questions? Okay. So we also, this week, you're going to have the week 10 assignment, the binary search tree assignment. And I just want to remind you that this is a particularly important assignment, both in that it's worth a lot of points and that the subsequent assignments are going to be directly building on this assignment and building on it differently than how we're building off of, say, the Unicode assignment or the iterative assignment. Not only will these future assignments be in the same repository, but they will be dependent on the code that you're writing for this assignment. So it's a particularly important one to complete. If you had to choose about which one to get in on time for this week, because you have a lot to do, then I would prioritize the BST assignment over the Twitter assignment. But either way, the late penalty, remember in this class, it's not too steep. It's only -10% per day late. So if you have to take an additional day or two to work on it, that would be better than turning it in incomplete. Also, so this is entirely okay, but I just wanted to point out that the lab attendance has been relatively low recently, and it's not required to attend. So not trying to guilt anybody into attending if you don't feel a need to, but I just want to remind you that I'm going to be less available to answer questions over the weekend and on Friday on GitHub issues. Probably won't be able to respond to those questions just because of taking care of the baby. So the lab this week is going to be the main opportunity that you'll have to ask questions before the due date. Also, so I noticed looking through the grades for the last 2 weeks that there were a lot of zeros because of students not submitting into Sakai your homeworks. And so I recommend that you all just double check in Sakai what your grade is for those assignments and make sure that if you completed it, it's really easy to push it up to GitHub and then forget to submit it into Sakai as well. Just double check that you've done that. And if you haven't done that, let me know so that I can regrade your assignments. And then the last thing is that, so this is not necessarily for this week, but since we're talking about all the grades and assignments, you do have required readings and viewings for this class. You just have to get those completed by the end of semester, the end of finals week, and reply to this comment or this thread right over here after you've completed that. Any questions about anything administrative in this class? Okay, then we will talk about binary search trees now. And so let's come over, here we go, to our images that we were working with before. And here, what we have is everything that we talked about last time. We were talking about binary trees and not necessarily binary search trees. A binary search tree is a special type of binary tree that satisfies an additional property that we call the binary search tree property, or the BST property. BST standing for binary search tree. And the BST property is that for every node, all nodes to the left, oops, I don't know what I was writing there, to the left will be less than or equal to, let's say for every node Q, will be less than or equal to Q, and all nodes to the right will be greater than or equal to Q. And so this is an additional property. Sometimes we call these properties invariants. And this is a property that every binary search tree must satisfy. We call it, when we are calling it an invariant, the reason we call it an invariant is because we say that the binary search tree will always satisfy this property. This is something that never varies about a binary search tree. There are other things that vary, like the number of elements inside of it, the height, things like that. But this property never varies. It always holds true. And so we'll see an example next, and then we'll see why this is a good property for a binary tree to have. So the tree that I'll draw, we'll do a 10 as our root, and then a 5, and a 3, and a 7, 6, 8, like this. Connecting all of these nodes with edges or branches. And then go in numbers, not letters. Say this is 15. And then 18 down here. So this is both a binary tree and a binary search tree. Every binary search tree is a binary tree, but not every binary tree is a binary search tree. It satisfies the property that if you pick any particular node, so we call this node right here Q, then everything to the left, all the nodes to the left are going to be less than or equal to, and all the nodes to the right are going to be greater than or equal to. One of the common misconceptions that people make about these invariants for data structures is that you only think about it in terms of the root of the tree. So this is true if we select this to be Q, but it's true no matter what node we select to be Q. So I'm going to do an orange, say make label this 7 as the Q right here, and everything to the left of that 7 is less than, and everything to the right of that 7 is greater than. And the thing that makes this a binary search tree is that this property, this BST property, it doesn't just hold for the root, it holds for every node in the tree. It holds for this 7, holds for this 10, holds for this 5, this 3, this 6, 8, 15, 18, holds for all of the nodes. Another thing that's a little bit subtle is that, so if we made this 15 right here our Q, then there is nothing to the left. So there are no nodes to the left. And so we would say it's vacuously true that all nodes to the left are less than or equal to Q, because there just are no nodes to the left. And then we have one node to the right, and it's greater than. So that's why it holds for this Q as well. Similarly, if you pick any leaf node to be our Q, then it's the binary search tree property, or the binary search tree invariant is going to hold for the leaf nodes. And we would say it's vacuously true because there are no subtrees, no sets of nodes to the left and right for us to check. So it must be true. Another common mistake that people make with these invariants is that rather than thinking about the entire subtree like this, you think about only one level of the subtree at a time. So up here is a valid binary search tree. I'm now going to draw an invalid binary search tree that many people might naively think is valid. So the following is invalid, but up here is valid. So in my invalid binary search tree, what I'm going to do is we'll make it very similar to the tree up here. We'll have a 10, scroll down just a little bit, and then 15, 18. So this part all looks the same. And then we'll have a 5 and a 7 and a 6 and a 3. And then the only thing that's going to be different, I'll draw in red to highlight it. The only thing that's going to be different is this node right here where I'll put an 11. And you can see that if you were to only, when we're thinking about this binary search tree property, if you look at one particular node and only look at its children, well, the children, 5 is less than 10, 15 is greater than 10. So it seems like we might satisfy the binary search tree property for this node, but in fact we don't, because if we look at all of the nodes less than 10, all of the nodes less than 10, this 11 right here is greater than 10. So this causes us to not satisfy. Does not satisfy BST property. Are there any questions about that?
So does the right node always have to fall between the range of like the parent node and the previous right node? Like that 11 node would have to fall between 5 and 7.
So this 11 right here would have to be between 7 and 10.
Oh wait. Oh yeah. Okay.
Any valid 7 to 10 would be correct.
Okay.
Maybe, so one other sort of subtlety is that, let's say we were only, I'm going to just draw around this section right here, only consider these, like this subtree of this entire tree. This subtree is a valid binary search tree, and the only thing that makes it invalid is when we add things on top of it. So it's, you can have valid subtrees inside of invalid binary search trees. And it's this structure outside of the tree which causes it to be invalid. So this is sort of like the key thing to remember about binary search trees and why binary search trees end up being really good for performance reasons. Let's say we want to find out whether a certain number is contained in a binary tree, so not a binary search tree. In a regular binary tree, so let's scroll up to some examples right here. In these binary trees, when we're at a node, we have no rule that can tell us where we should look for any particular number. There's no rule if we're at this 1 and we're looking for the number 5, we don't know whether we should go to the left tree or to the right tree to look for the number 5. But when we're in a binary search tree and we're starting at a root node and we're, say, looking again for the number 5, we can compare 5 to our current location. 5 is less than 10. So that means that we must, if there is a 5 in the tree, it must be contained to the left. And that means that we don't have to look at any of this stuff to the right when we're doing our lookup to see if something's contained in the tree. We call this a pruning algorithm because we can prune off this entire tree. We don't have to look at anything over here. And this should hopefully be seeming familiar to the binary search algorithm itself, where each step we looked at the left, compared whether the current location that we're at is less than or greater than what we're looking for, and go to the left or the right accordingly. This fact that we're able to prune off sort of entire branches of the tree, entire subtrees at each iteration of our search is what's going to make binary search trees fast on these insert look operations. So the algorithm, fairly intuitive. You start at a location. If the number you're searching for is less than that location, you go to the left. If it's greater than, go to the right. And you keep following that until you find your location.
So then when we make the child nodes, are we only considering the parent node? Like what if the 8 was like an 11 instead of an 8?
Yeah, so if the 8 was 11 instead of an 8, then we would not have a binary
Right.
search tree. We would just have a binary tree. And so at this point, we haven't talked about how do you actually create binary trees. We've only talked about somebody's magically somehow given you a valid binary search tree. What can you do with it? And the answer is that you can do this fast search with it. But yeah, like in this example right here, let's say we were to search for 11. Well, 11 is in this left subtree, but when we're at this 10 location, we would see 11 is greater than 10. So we would go to the right, check 11 against 15, see 11 is less than 15, look for the left. There's nothing to the left of 15. So we would say there's no 11 inside of this binary search tree, but we would in fact be wrong because we do not satisfy the BST invariant. Great question. Any other questions so far? Okay. So that's how the sort of main operation that you might want to do inside of binary search tree is that lookup operation. Another operation that you might want to do is finding the minimum or the max of a tree. And this is something else that we can also do really efficiently in a binary search tree. If we're trying to find, say, the minimum, then you start at the root and always keep going to the left. So keep going left. So if we wanted to find the minimum of, well, that's not a valid tree, but this tree right here, the minimum right here, we start at 10, go to the left, go to 5. Now at 5, go to left, we're at 3. There's nothing to the left of 3, so that means we must be at the minimum of this tree. 3 is the minimum. Similarly, if we wanted to find the maximum, you start at the root, you go to the right, and then you go to the right. And now there's nothing else to the right, so this must be the maximum of the binary search tree. all of these operations can be done really, really efficiently. So keep going left for min or right for the max until you get to the end and you can't do that anymore. Any questions about either of these operations, looking up, finding min or max? Again, I'll just mention that the textbook is pretty good in this section, and they have both formal like pseudocode for each of these algorithms and actual Python code that you can reference. So that's why here I'm going at a little bit higher level, just trying to help you capture the intuition for each of these operations. Any questions so far? Okay. So then the next operation that we might want to do on a binary search tree is insert a new item into the binary search tree. And this is important because this is how we're actually going to construct a binary search tree. In order to construct one from scratch, you'll just, if we had, say, a list of items that we're trying to create as a binary search tree, we just add those items one by one into the tree. So let's see, how do we add a number into, say, this tree right here? There's my cursor. So how to add. The first thing that we do is we do a binary search. So use the find operation to find the to find a leaf. So use my pen is being very laggy right now. Use binary search to find a leaf. So let's say I wanted to add the number 4 in this tree over here. I'm going to add the number 4. Well, I'm going to do binary search with the number 4. So is 4 less than or greater than 10? It's less than, so I'll go over here. Is 4 less than or greater than 5? It's less than, so I'll go over here. And now I have found a leaf node. And now that I'm at a leaf node, I will create a new child for this leaf node. Because my particular example 4 was greater than 3, I'll add it as a right child. Add as a left or right child to satisfy the BST property. So the maybe one of the things to start like thinking about as we're talking about these data structures and the different operations that you can do on them is starting to think about like the complexity of each operation and which operations are the simplest ones. Those are the ones that you probably want to implement first, and which ones are a little bit more complicated. And we can see that as a subroutine of adding, one of the things that we have to be able to do is do a binary search. So you definitely want to, in your homework assignment, implement the finding ability or the binary search ability before implementing the add ability. In the test cases, which we'll look at in a little bit, there are several sets of test cases. In some test cases, it's creating a binary search for you manually, or a binary search tree for you manually, similarly to how we created a binary tree manually. And because we have those manual construction technique, you don't have to have the insert method implemented before you work on the binary search method. So you definitely want to do this before doing the add. And once you get this working, you can basically just copy and paste your code for the binary search with one additional statement at the end that's going to actually add this node to the tree. Let's see, one other subtlety about the add operation. Let's say instead of a 4, I want to add a 13. So 13 example, right here at the 10, we go to the right because 13 is greater than 10. Here we get 15. We're comparing against 15. 13 is less than 15, so we'll try to go to the left. And even though I'm not at a leaf node at this point, when I go to the left, there is no subtree right here, and so I would add 13 to the left right here. So it doesn't necessarily have to be a leaf node. It's just a node where you can't continue going anymore, searching for whatever number that you're looking for. There's the 13 right there, and let's add the 4 right over there. Are there any questions about the intuition about this adding procedure, how you add things to the tree?
Yeah, Mike. So when we're finding, I'm a bit confused about the finding step since we're not looking for an exact number. What exactly are we finding for?
You're searching for the number that you're inserting. So when I was doing 13, I was searching for the number 13. So comparing 13 to 10, 13 is greater than 10, so we go right. Comparing 13 to 15, 13 is less than 15, so we would try to go left. But before I drew this here, there was no node to the left, and so we would not be able to go left, and so that's why we added the 13 right here. The ultimate sort of, maybe another way to think about this is that what we're trying to do is make it so that when somebody searches for whatever number we're looking for, then they're going to find that number. So all of the procedure starts with the same search procedure for the number we're inserting. If we're inserting 13, we first go right, then we go left. And then once we've found the spot where the number should be, but is not yet, we insert it. So this use binary search, the thing that we're searching for is the number that we're inserting.
Are there never any repeats in binary search trees?
That's a
Like
great
you'll
question.
never find 2, 13.
Fantastic question. The question's, what about if, say, the number was already inserted? All the examples that we did so far were for unique numbers. What if we have a duplicate value? And the answer is that so a binary search tree is sort of like there are many specific types of binary search trees. Some allow duplicates, some do not allow duplicates. In your homework assignment, you're allowed to do it either way, either allowing a duplicate or not allowing a duplicate. The easiest thing to do is to just not allow duplicates. And in that case, so if there's a duplicate, so if in this step right here, you actually found the number that you were looking for, then you just do nothing. So if it's a duplicate, which is equivalent to if you found the number in the search step, then do nothing. And so if we were to say reinsert the number 13, we would start at 10. 13 is greater than 10, so we go right. Find 15, 13 is less than 15, go left. We found 13, so then we can do nothing. Great question so far. Any other questions? Okay, the last operation that is important for your binary search trees is the deleting or removing values from a binary search tree. And this is going to be by far the most complicated of the operations. So this is going to be the one that when you're implementing things, definitely save this one till the very end. And I'm gonna scroll up here. We got a blank page, and right here. The values that I had before, I think, was 10, 5, 3, 7, 6, 8, 15, 18, something like this. And rather than drawing circles around everything, I'll just leave them outside of circles like this. You'll see people draw trees both ways. And there's the first step of the delete algorithm is the same as the insert algorithm or the binary search algorithm. First step for delete is just find the node. And you use the binary search procedure to find the node. So let's say we're going to, as our first example, delete a 6. Example 1, delete a 6. 6 is less than 10, so we go to the left. 6 is greater than 5, so we go to the right. 6 is less than 7, so we go to the left, and we found our 6. At this point, we have several cases that, that can happen. Case 1, we're at a leaf node. In this case, the intuition is it's really simple. You just delete the node. There's nothing special that you have to do. Leaf node, comma, just delete it. So I'll X out this 6 right here because we've just deleted it. In practice, how do you actually encode just delete it? You would say that your the 7 node, so I'll say 7 node, or more generally, the parent node, dot left equals none. So previously, the parent node dot left was equal to some other node instance, and by setting it equal to none, that just deletes it from the tree, so that next time when we go through the tree and hit this 7 spot, we'll look at the left child and we'll say that none, there's nothing there. The next cases are going to be significantly more complicated than this case 1. So now's a good time for us to pause and see if there's any questions about what to do in this case 1. Okay, so case 2. The node is not a leaf node. So let's we'll just say not a leaf node or internal node. And our example is going to be, we're going to delete the number 5. So here, we've deleted the number 5, and, or let's see, first we have to find the number 5, so 5 is less than 10, we go to the left, and now we have found 5 in the middle of the tree. So not a leaf, we're in the middle. Now the question is, what do we do? Well, if we did this same operation that we did before in our leaf node case, setting the parent node, in this case parent node dot left equals to none, then not only would we delete the 5, but we would delete the 5 and this entire subtree over here, because then there would be no way to go from this 10 down to say the 7 or the 10 to the 3. So it's not acceptable to just set this node equal to none. Instead, we have to replace it with a certain value. Now the question is, what do we replace it with? Well, one thing that might be potentially something that you would think about is let's just replace it with one of the children. So in this case, we could take this 3 and move it up to the 5, and we would get something that looks like 10 down to 3 over to 7 over to 8. And that is still, that now gives us a valid binary search tree. This would be a valid thing to do, taking this child and replacing it with 5. But what if this 3 also had some children of its own? So what if this 3 had a 4 and a 2 like that? It's a perfectly valid thing that could happen in a binary search tree. This is a valid binary search tree in green that I've drawn down here. And now when we tried to move this 3 up to this 5, well, we'd have a left child of a 2 over here. That'd be okay. But what would we do with this right child of 4? We would be trying to have 2 right children of 4. So this is a problem. This 4 and this 7 can't both be the right child of 3. So our first idea of reusing a child, replace with a child, does not work. This is a common thing for people when they're coding up solutions to binary search trees. To even though, so in a second here, I'm going to explain what the correct solution is. Even when people can describe the correct solution on like pictures and whiteboard it out, I'd say what I'm doing right now is whiteboarding out the algorithm of just drawing the structures and what they're supposed to look like. Even when people get this part correctly in the intuition, they still try to code up this as the implementation for case 2. And so this is a very common mistake for doing that. So I'm highlighting it right now just as an emphasis of this is incorrect. Do not try to replace the child. When you delete something from the middle, do not try to replace it with a child. Instead, the correct solution is find the smallest or largest, so the min or max node of the node that you're trying to delete, as the first step. And here it doesn't matter whether you choose smallest or largest, doesn't matter. And once you find this smallest or largest node, this smallest or largest node is guaranteed to have no children. We saw before that the algorithm for finding the smallest or largest node is that you keep going all the way to the left until you can't go to the left anymore, or keep going all the way to the right until you can't go all the way to the right anymore. And once you do that, you can replace your node. So let's say replace this 2 up here, or we're in this situation right here. We have this 5. We're trying to delete this 5. Instead of replacing it with the 3, we delete this 2, finding the smallest, delete this 2, and replace this 5 with a 2. Now we will, apologize for that. That's a typo on my part. That is my sleep-deprived baby brain doing something almost correct, but slightly not correct. What I was doing was finding the smallest child of this 5 overall, and doing that, moving this 2 up here, is not going to give us a valid binary search tree, because if we have the 2 right here, then this 3 which is greater than the 2 is to the left. That's incorrect. What we need is either the smallest child of the right subtree or the largest child of the left subtree. So we need to move either the largest of this left subtree up here, or the smallest of this right subtree up here. So let me, since I misspoke earlier, I will rerun through this and re-explain, rewrite out and re-explain the steps. So you find the smallest, largest node, not of the node you're trying to delete, but of the, so the smallest node of the right subtree, smallest node of the right subtree, or the largest node of the left subtree. Smallest node of the right subtree or the largest node of the left subtree. Up here, the largest node of the left subtree is guaranteed to be bigger than everything else in this subtree to the left. And so we can move it up, and we're guaranteed to continue with the binary search tree property. The similarly thing would happen if it's the smallest on the right subtree, then we move it up and it's guaranteed to be smaller than everything that's on the right subtree. This is what happens when we have 2 children like this. We move things up. But now there's one last case of what happens when we only have a single child. So here, if this 6 was still a valid node, sorry, the 6 is not a valid node, and so the smallest child of this right subtree, the smallest value in this right subtree is this 7. And if we tried to delete this 7, it's not a child node, so we can't just delete it without consequences. We delete it and move the 8 up. Let's see. Apologize that my space has been formatted poorly here, but the case 3, when we have a situation that looks like 5, 7, 8, deleting something from the middle with one child, either one right child or one left child like this. Delete the node and replace it with its child. So I'll run through that example, run through all 3 cases one more time here in a second. But the first thing that is hopefully apparent is that this deleting operation is significantly more complicated than all the other operations. And so this is the last one that, that you want to implement. That if you can't do the other operations correctly, you're not going to be able to do this deleting operation correctly. When you do this deleting operation, you always, the first thing is you find the node that you want to delete in the tree. Once you've found that node, then you're into 3 cases. The first case is when there are no children in the node and you can just instantly delete it. When there's no children in the node, you just instantly delete it. The second case is if you're in this internal node that has 2 different children, then you can't just delete it, because what do you do with the children? And so in that case, you find the largest value of the left subtree or the smallest value of the right subtree, delete that value, and move it up into this location. The final case is when you don't have two branches, but you only have a single branch. And in that case, you can just delete the node, but you have to move the child, whether it's a left child or a right child, replace it so that this becomes 5 to 8, or this becomes 5 to 6. Are there any questions about the, let's see. At this point, it's definitely okay if you have questions about how, like, coding-wise, how to go about implementing any of these algorithms in code. At this point, what you want to understand is, say, like the diagrams, the whiteboards, that if you were to draw out a binary search tree and I asked you to either insert or delete on that binary search tree, could you manually go through the procedure and draw what the resulting binary search tree should look like? Are there any questions about that? Okay. So what we're going to do next is take a look at some code and how to do this. And in let's see. So we don't have enough time left to do as much of the looking at the code as I would like to. So I'll go ahead and do a little bit of an extension on this assignment for everybody until so give everybody a 3-day extension so that Wednesday is the standard due date for the assignment, and then Friday with the 2-day extension, and we'll have a chance to do a little bit more code related to this on Monday, but we'll start talking about some of the code today. So here I have opened up to our containers folder, the binary search tree branch, and if we do ls containers, recall that there are two different Python files, this binarytree.py and this bst.py, and the binary tree file, binary tree, is what we looked at last time, so we'll look at the bst.py this time. Down here, I'm going to do Python 3 containers / bst.py and do this in interactive mode. And if I do this, you'll notice that we get this error message down here. So this is going to make debugging a little bit more difficult in this bst file than it is in the binary tree file. In order to see why this error message is coming out, in the top, I'm going to open up in Vim this bst file. So Vim containers / bst.py. And the error message happens here on line 6. That in this file, because every binary search tree is a binary tree, I am importing our node class and our binary tree class from this containers.binarytree file. This error message down here, what it's saying is that we get this module not found error, no module named containers. And this is due to the way that I am invoking Python down here on the command line. One of the things that is sort of widely disliked about Python is that it's very difficult to understand where Python is looking for files when it's doing these imports. The way that things are supposed to work is that anything to the left of a dot is a folder, anything to the right at the very end, the lastmost thing is a file name. So this binary tree, containers.binary tree, is supposed to refer to this containers/binary tree file right here, containers/binary tree. It's supposed to refer to this file right here. But when we invoke Python like this, with this -i flag in particular, it doesn't know that that this is where it's supposed to look. When you use this -i flag, internally what Python is doing is it's first cding into the containers folder and then doing python3 bst.py like this. And you can see that this also gives us this same error message, no module named containers. And that's because once we're inside of this containers folder, there is no further containers folder for us to go inside of and look at. When you're debugging, you won't be able to use this -i flag. You'll have to do python3 space containers/bst.py. Like, oops, sorry. You'll have to do python3 -i. And then once you're inside of Python, so notice that here, I did not specify a file name on the path. I just said python3 -i. Inside of here, I said import containers.bst like this, and import containers.binary tree like this. Once you've started Python like this, then you can import these files, and then you can do containers.binary tree, say getting the node class, like that, get the node class, or you can do containers.bst, and then inside of the bst file, there's a bst class.bst like this to get access to the bst class. So this is one of the reasons too why it's important never to cd out of your project's root folder, because if you do that, you won't be able to correctly import any of your files. If we were to cd into containers like this and now do python3 and try to do import containers.binary tree, that won't work. We could do import binary tree like this, but if we try to do import bst, now that won't work because bst relies on the fact that it can access this binary tree like this. So don't cd. And when you do load these files, just python3 -i by itself. Inside of this BST class there's a number of functions that you'll have to implement. The first is this constructor function, and I'm going to go ahead and implement this function right here for you. So this constructor function is a little bit different than the constructor from our binary tree in a couple of subtle ways. So /binary tree, let's go ahead, there we go. And the first is that down here in the binary tree constructor function, you notice that we're passing in the ability to have a single node value, just one node. The reason for that is because in the binary tree, there is no generic insert method. There's no generic way to insert, say, 100 things at a time, because we have no rule to follow about what should the resulting tree structure look like. In the BST class, however, it is possible to insert multiple things at once. And so here we're passing in an entire list and not just a single value. So that's the first difference. The second difference is related to this code that I already have down here. And this is closely related to this up here. In this syntax up here on line 9, when I'm creating a class BST like this, what I'm saying is that, or the Python language for this is that BST is a superclass, or sorry, BST is a subclass of binary tree, and binary tree is the superclass of BST. That means that BST will have access to all of the functions inside of the binary tree. If we come back over here to binary tree, recall that there's a lot of functions that you're going to be implementing in here, like this print tree. We talked about this a lot last time, these different traversal types that you can do. And a binary search tree, because a binary search tree is a binary tree, you'll have access to all of those functions sort of for free. You'll be able to do your traversal of the binary search tree just like it was a binary tree. One of the nice properties about a binary search tree, which you should try to think about and justify this to yourself, but an in-order traversal, sorry, an in-order traversal of a binary search tree will return results in sorted order. So based on our discussion of an in-order traversal and the binary search tree property, you should be able to combine those together to make this statement make sense to you. That's a good way to check your understanding of everything that we've talked about so far. The one implication of this is that we have actually just discovered and created an entirely new search algorithm, or an entirely new sorting algorithm. We've created a new sorting algorithm, and that is put everything in a BST, then do an in-order traversal, and you get out a sorted list. So that's the benefits of having binary tree be the superclass of BST, or BST be the subclass of binary tree. This, anytime you have this sort of construction on your class definition up here, the very first line in your constructor should always be something like this. What this is doing is it's calling the constructor of the superclass, that this super function will return the binary tree, and then it'll call the init function on binary tree. In this case, the init function on binary tree doesn't really do much, so we could get away without doing this, but it's just a good habit, good thing to do. The next thing, let's see, so what we're trying to do here is insert, what this constructor needs to do is insert all of the elements inside of this XS list. And so let's scroll down a little bit, and we have this insert list function down here. Given a list XS, insert each element of XS into self. And so the correct implementation of the constructor up here is just self dot insert list XS, like that. Whatever gets passed in here, pass it to the insert list, and that'll do it. The insert list function is also really easy to implement. You'll just, for each x in XS, self.insert x. Repeatedly call the insert method, inserting it for each entry in XS. The key difficult part will be actually inserting this, or implementing this insert function right here. Yeah, at this point, you can get started on everything in the binary tree file itself, and but we'll go over a little bit more of this binary search tree, do some examples of creating these recursive functions that do these searches in class on Monday. So that's the official end of class today, and I'll stick around to answer questions in office hours now. Otherwise, I'll see you either in lab tomorrow or on Monday.